All right, now we're going to move into our panel discussion. So I'd like all the speakers to enable their cameras and mics. I'll be starting with a few questions of my own, and then we'll take some questions from the audience Q&A. Please go ahead and submit your questions using the Q&A button at any time, and we'll take as many as possible later in the session. So Sean, you mentioned that you're already working with customers on the hardware. How soon do you expect to be able to support production shipments of the new system?
So we've been shipping production systems since Q4 of last year. That's when we announced our first customer. And so we've obviously had the wafer and the system working in our labs for some time before that. But really over the last 3 to 6 months or so, we've started to ship to customers, and it's been really fulfilling seeing our customers solving real problems on our system, especially those that are they couldn't solve before or were very challenging to solve on GPUs today.
Right, right. And do you plan to publish some benchmarks for the ML perf training at some point?
We do. We believe very strongly that standard benchmarks such as ML perf are really important to the industry. However, benchmarks do require some amount of effort and sometimes require some specific tuning. So we haven't really been focused much on ML perf, and we've been focused most of our attention on some of our early customers and getting those up and running. And our customers are seeing their networks run, sometimes hundreds of times faster than on a single GPU.
Great, great. Dennis, how soon do you expect to have the TSP available to customers?
Sure. So we expect to be delivering in volume in June of this year. So we've been sampling the hardware to some early customers and building out the various layers of the software stack. And as you can imagine, that's an ongoing maturation process. And as Sean indicated, these things take effort and time. And so focusing on not only the customers' models and customer goals, but it also takes time to be able to do ML perf, for example, to be able to provide some apples to apples comparison and some support for the broader community.
Right, right. And Ljubisa, you mentioned you guys are sampling already. Do you have a goal for production shipments?
Yeah, so we're in engineering sample mode at this point, and we're aiming to be able to support volume production kind of early fall timeframe. We don't quite have an exact month pegged. We've been making a lot of progress, not only in bringing up workloads and things that we do in our lab, but also other necessary parts of the flow, like the ATE flow is up and running. We're almost there with wafer sort and the more production oriented things. So that's all happening and aiming at, essentially a matter of several months.
Great, great work. So, listening to the three presentations, I was struck by some big differences in the architecture approaches. Dennis, maybe you could talk about a little bit more about why you guys chose to have one big core versus a lot of little cores, like we heard from the other presenters.
Sure. Yeah, we took a decidedly different approach in that the entire chip is effectively treated as one big logical core, and that the principal goal there was to eliminate, to do so in a synchronization-free way. So as you can imagine, when you're trying to expose thread level parallelism, threads find some amount of work, and then they have to occasionally do a barrier synchronization to exchange that amount of work or exchange the results across a boundary condition. And that introduces, of course, latency and latency variance, and to be precise. So I spent a lot of years at Google chasing down kind of the 99% tail latency. It's a big problem in internet scale applications, and you can imagine it's a big problem trying to deploy these kind of models at large scale. So in large part, our goal was to really avoid the kind of communication overhead that goes along with barrier synchronization to coordinate what amounts to, in many cases, thousands of threads in order to get good utilization on these highly parallel, fine-grained many-core architectures.
So then, what is the end application benefit from that decision?
So the end application benefit is we really take this approach where we sprint to completion, and so the end application benefit is very low latency. So this is also energy optimal in the sense of you start the inference and you sprint to completion, and then you go idle, and it allows you to like I said, that sprint to completion is optimal from an SLA perspective, but also in an energy sense. You're not wasting time and energy in the process. So we think that has a very first order effect of latency, and we see that with our ResNet numbers, right? A forward pass of the ResNet network is less than 50 microseconds. So
right.
that's the direct benefit, is low latency.
Low latency, right. So Sean, you guys took pretty much the opposite approach with hundreds of thousands of tiny cores. What is the end application benefit there?
So ultimately, the way that we think about the final end goal is to be able to get lower total time to train, right? That's the end goal. It's not about how many peak flops that you have. It's not about the number of cores that you have, but it's really about what's the total time to train and how can we reduce that. And so when we looked at the workload, I spoke about it in my talk. There's a lot of sparsity. Sparsity introduces a lot of very dynamic, fine-grained behavior, which is very hard to harvest using big, large monolithic cores. And also it was in the Tenstorrent talk as well. There's other sources of dynamicism that occurs in these networks, such as different sequence lengths, right? You can almost think of that as sparsity in the sequence dimension in some sense, right? Again, highly fine-grained, highly dynamic, and I think that's the that's the trade-off that we're all kind of struggling with right now, right? Is if the workload is so dynamic, you can build very large, very high flop count matrix engines, but the utilization won't be very high, right? And so that's the reason that we went in the direction that we went.
Okay, and whereas Dennis was stressing the latency in your case, I mean, for training, you're really looking at throughput rather than latency.
That's true. I mean, we're primarily optimizing for throughput. I don't think this is necessarily a byproduct of the many core architecture, but because of our memory architecture, we also are optimized to run at batch size 1. And so it turns out as kind of a side effect that we also have low latency. But I wouldn't say that was a direct result of the many small cores, right? More the memory architecture that we chose. Right.
And Ljubisa, with the Tensix architecture, you've kind of taken a middle ground in terms of the size of the core, the number of cores. What led you to that decision, and how does that affect your ability to deliver high performance?
So between the viewpoints that were already stated, I tend to kind of agree with a lot with what Sean has said. So that due to the fact that there's a lot of dynamism in the workload that manifests, a couple of different ways, as well as the fact that over the last couple of years, tensor shapes and the dimensions of these things that make up neural networks that are currently popular have varied a lot. Building basically huge sort of monolithic gem engines has become a source of some inflexibility with, with an eye towards these two things. So a bunch of small cores, came out partially out of that kind of thought process. The other one is essentially scale, right? So you eventually have to get to a point where you're putting down multiple compute engines, even if they are big gem engines, and at that point you have to deal with synchronization, and ideally you want to avoid the barriers that Dennis touched on, and there are solutions that do to various degrees succeed at that. So my thinking and the thinking of the Tenstorrent team was that we're better off prefetching that problem than like kicking it down the road kind of thing. The final aspect of it is flexibility from a deployment standpoint. So from the get-go, we wanted to be able to do a small edge chip eventually. Now, if your building block is a massive 500 millimeter, array, it becomes a massive effort to redesign to these smaller, deployments. So ultimately, to your question, why we went, to the middle ground here, it's primarily because we wanted to hit a particular teraops per watt point, because we had the target of fairly low power, deployments to begin with, and the portion to hitting that has to do with how many, sort of primitives of math you perform per software visible instruction. So essentially, we ended up with these fairly heavyweight cores, purely to basically drive up raw teraops per watt, right? But aside from that, philosophically, a bunch of small cores is more sort of compatible with our thought process than many fewer large ones, for the reasons stated above.
Great. Yeah, thanks. Yeah, I wanted to start taking some audience questions so we can get as many of those in as possible. Dennis, question, does your compiler handle parallelizing the code across all the different units in the chip?
Great question. So yeah, so the Groq chip uses this flat shared scratchpad memory. So our memory is not kind of partitioned and spread out all over the chip. It's really a large central shared low latency structure that is shared across the functional units within the device. And the low level programming abstraction allows us to take tensors and not only spread it across multiple banks within the same chip, but we can take those tensors, for example, and spread them across multiple chips as well. So there's support to be able to take model parallelism and exploit that, as well as just taking advantage of the data parallelism within the tensor. So as part of that is, and I think we've kind of touched on this, is that memory system design is really central to being able to provide the kind of memory concurrency requirements, and all these kind of parallel architectures really. And when you lay out a parallel algorithm, it really starts with first principles in terms of what are the memory concurrency requirements, and laying that out really drives a lot of the other decisions for the parallel algorithm.
Okay, thanks, Dennis. Sean, a few audience members are asking about yields. So how do you manage the yield across such a large chip?
That's a great question. Clearly, yield is a problem even for traditionally large chips that are nearing reticle size, even in mature technology processes, defects in manufacturing are just a fact of life. We would be yielding zero if we needed an entire wafer with zero defects. And so to solve that, we actually built into the hardware itself redundancy mechanisms that would allow us to detect and map out bad cores and fabric links that have defects in them. And then in the hardware itself, we can recover those and route around those defects such that it still presents itself to the low-level software as if it's a fully uniform 2D mesh. The concepts are similar to mechanisms that have been used in memory architectures, right? Very much leveraging the uniform nature of the architecture, so that we can easily detect and map out defects. And we do this in the hardware itself. And once we do that, we can actually get yields that are actually pretty high. And the reason for that is that most fab defects are fairly localized and randomly distributed. And so by using a technique like this, we can actually get yields even higher than the regular chips that I've worked on in the past.
Great. Ljubisa, you mentioned some performance numbers in your talk. Are those numbers compliant with MLPerf rules?
So the ML, I guess I'll answer the question with a couple of sub answers. So MLPerf inference rules are that if you can perform inference which yields results that are within 1% of kind of quality of results, so what you get running floating point numbers on a CPU, it's acceptable, roughly speaking. So, or at least that's my understanding. I know there's MLPerf people here in the call. You can jump in and correct if I'm wrong. So with that kind of mindset out of the table that I've shown for BERT, the first two lines clearly accomplish that. So essentially, the apples to apples just run through the network. That's just a floating point run of BERT, and there's no controversy there. The conditional computation bullet combined two sort of fairly lightweight conditional computation features. One was this dynamic sequence length thing, which doesn't change results at all. The other one was early exit, which we've deployed to a point where its impact on quality of results is less than 0.5%. So a good deal better than MLPerf rules. Now, the third line in the table, which had about a twice as high number as the middle line in the 20,000 range, essentially, we deeply believe that we will get it to a point where it's compliant to MLPerf rules, but as of today, it's a little bit out. So like it hurts the quality of results. Like the current state of this work in our lab is such that if we took it to MLPerf now, it would not be meeting the sub 1% rule.
Right. But then people could trade off the accuracy for the throughput.
Not only that, but I believe that we'll get it there. There's really no reason not to. Like, so, we're essentially, a lot of this stuff is hot off the press as far as we're concerned. The chip's only been in the lab for about 3 months, so there's a lot of work going on. So I think we'll get there. But I think the key message that I wanted to leave people with is not so much, sort of exactly whether it's 1% or no, even not so much the results on BERT, which is unmodified, as much as the fact that this is a fairly large dimension to exploit, which we've only started touching, that I believe will provide a way to really make some serious headway for machine learning as a field.
Right.
Yeah. So I guess the second, sorry there, Linley, I just wanted to state one more thing. The second part of the answer, and that's that so for early exit, we're kind of, there's a change. So we're not modifying BERT, but we are modifying the entire solution, right? So MLPerf has actually not comprehended, this kind of approach to the problem at all. As a result, I'm not sure that the whole approach would be acceptable, because depending on how you view, BERT, on the one end, we didn't change BERT the model, on the other, we added something that sort of makes it not quite BERT, for that line. So that's something that I would invite MLPerf people to perhaps think about in terms of, a way to comprehend this kind of story in future versions of the benchmark. Right.
Yeah. And Dennis, same question for, you mentioned some ResNet 50 numbers there. Are those fully MLPerf compliant?
I think we plan on submitting in this upcoming is upcoming. I think there's a June submission as well. But I believe they are. The one exception there is we just downloaded ResNet v2 instead of v1.5. But we just literally took the vanilla ResNet and used that. So I believe we will be ready to submit to MLPerf at least in the near future.
Right. And Dennis, the TSP has quite a bit of RAM on the chip, 220 megabytes. But since you don't have any DRAM interface, how do you handle models that are larger than that?
Great question. So a couple of things. We've got a lot of RAM on the chip, which means we also need to be concerned about not only yield but also protection from bit upsets, so single bit errors. So all of our memory and our data paths are SecDed protected. But not only that, we to be able to grow beyond the size or the memory capacity of a single chip. If remember, I showed a die photo, and along the die photo was ringed with our SerDes around the external of the package, and that is because we have 16 links that allow us to effectively build glueless multiprocessors by interconnecting these chips in a direct topology, and that includes mesh and torus, as well as generalized hypercube. So we support a number of interconnection networks to be able to scale and grow beyond a single chip, and we've got dense packaging solutions that allows us to pack multiple of these cards within a small area, so that we can build racks of these systems that are performant and can, like you said, strongly scale across multiple devices.
Right. Sean, you mentioned sparsity. There's a question about what is the typical sparsity percentages that you're seeing in the workloads that you're using, and is it really enough to make it worth building sparsity-oriented hardware?
So we're seeing naturally occurring sparsity very oftentimes in the 2 to 5x range. And of course, as with any of these things, it's very, very workload dependent, right? Certain networks naturally have very low sparsity, and others we've seen as high as almost 10x sparsity, even just naturally occurring, meaning that there's only 10% of the values are non-zero, and so it's obviously kind of across the board. Now the reason why ultimately we believe that this makes sense is twofold. One is that we believe that even if the models are dense, the architecture runs it just fine, right? And so in some ways, having a sparse capable hardware is a bit of a superset, right? So long as the additional mechanisms you're adding are not that high, right? In terms of cost. And then the second is that I mentioned this briefly in the talk as well, is that I believe there's a large untapped potential for sparsity because there's no hardware today, right? The ML methods naturally are sparse, and today all the sparsity that I just mentioned comes about because it makes the ML better, right? Not with no consideration of the performance on the hardware, and I believe that once you have hardware that's able to exploit the sparsity, it will actually enable the ML user to explore all sorts of ML techniques that will induce sparsity that they would not even think about today, right? And so it's for those two reasons that we believe that this makes a lot of sense.
Great, thanks, Sean. And a question for Ljubisa. Is the Grayskull support for conditional computing only in software, or are there hardware-specific optimizations to enable this feature?
So it's very much a full stack statement, you know, to basically enable finer grained conditional computation. So to the points that we already discussed, if your basic building block to the hardware that you bring to bear is let's say you know, a 1024 by 1024 matrix multiplier, or even a, you know, a 128 by 128 one, there's really nothing that you can do on a grain that's lower than that. And even if you built the ability to do conditional computation or dynamic sparsity handling, you know, it's a statement that must be true at a level that's higher than that grain. So the hardware needs to be good and utilizable to a large extent with pretty small blocks, right? Like 16 by 16 or just 16, or like in general, there's a breaking point somewhere where if you make it too small, the hardware ends up being too inefficient and the price is too high. But you have to make the hardware, you know, with conditional in mind. And then on top of that, from the software standpoint, you know, think of things like balance across a machine that, you know, doesn't know which core is going to take how long up front. Memory management in the face of not knowing how big results are going to be up until you actually generate them. So these are all things that you need to solve in order to bring out a solution that does conditional computation or dynamic sparsity. Sure, they're basically somewhat related, right? Like, thus it's totally a full stack statement. So it needs to be from gates all the way up to the top of your infrastructural software stack.
Great, thanks, Ljubisa. That's all the time we have for questions. I'd like to thank our three speakers for their presentations today.
Thank you, Linley.
Thank you, Linley.
And everybody.
Thank you.